Hi, folks. Welcome to part two of this week's lesson. Let's just recall where we left off. We were trying to determine a way to define the points on a plane in 3-space. And what we saw is we could use this idea of using two basis vectors to allow us to describe any vector on the plane. All right, and then we combine that with the idea that we use when determining the vector equation of a line, that if we took a point to that plane, then added this linear combination of our basis vectors, we could get to any other point on the plane. Okay, and we had both this vector form, this parametric form. And it's quite nice because, again, it kind of recycles an idea that we've already seen and relatively easy to come up with. The problem that we talked about was that, you could use any two non-parallel vectors on the plane, and you can use any point on the plane. So depending on what information you use, you could have 2, 3, 4 people getting 2, 3, 4 very different looking equations. Okay, and just showing that those equations are the same actually takes quite a bit of work. And in fact, one of the questions we're going to do in the third video this week is show just how much work is needed just to find, say, the x-intercept of a plane. Okay, so these things motivate us to look for perhaps an alternative to the vector equation. So there are uses for the vector and certainly for the parametric equations of a plane, but this idea of there being too many versions of it give us sort of the impetus to try to find an alternative. Okay, and what I'm going to use as an alternative is, instead of dealing with vectors that are on this plane, in other words, what we call direction vectors, I'm going to work with what's called a normal vector. Okay, now if you remember back in calculus, sometimes it asks you to find the normal to a curve at a point, and that was just, the normal would have just been, if this was the tangent line, the normal would have just been the line that is perpendicular to it. Okay, so we're going to recycle this term because the normal vector is going to be a vector that's perpendicular to this plane. So some vector that is perpendicular to the plane. Okay, now the reason why this is going to work is that if I have some vector, okay, I realize that this vector, if you look at it, it's perpendicular to it. Well, this plane is not perpendicular. This plane is not perpendicular. There's only one direction of this plane that's always going to be perpendicular to that given vector that I have here. All right? So what I want you to think about is that not only is this vector perpendicular to the plane, it's also perpendicular to any vector on the plane. So we're going to draw that later on if you're having a hard time seeing it. But because this vector is perpendicular to the plane, any vector that's on the plane will also be perpendicular to this normal vector. That's going to be the key. Now there is a problem though, is that while this vector is perpendicular to this plane, it's also perpendicular to this plane, which is parallel to the original one, or to this one here, which is parallel to the original one. The same vector is perpendicular to all these parallel planes. So not surprisingly, as we've seen before, just having a vector isn't enough. I'm also going to need a point on the plane. Okay? But the idea here is I'm going to use the fact that this normal vector, because it's perpendicular to the plane, is perpendicular to any vector on this plane. Okay, just as I showed you before. Okay, but now if this is some given point on the plane, say x naught, y naught, z naught, okay, regardless of what point I'm working with on the plane, say some general point x, y, z, notice that the vector joining the given point to the general point, this vector, is going to be perpendicular to my normal vector, regardless of whether xyz is here, whether xyz is there, regardless of whether xyz is there. No matter where that second point on the plane is, the vector from the given point to that point will always be perpendicular to the normal vector. And this is going to be what I'm going to use to come up with an equation. Because I want you to think, what is special about two vectors that are perpendicular? What very special quality did we determine two perpendicular vectors had to have? And hopefully you're remembering that the dot product has to be 0. Okay? So no matter which vector I use on the plane, because it's always going to be perpendicular to that normal vector, I know the dot product between these vectors has to be 0. And this is going to be my my route to coming up with an alternative equation. Okay? So let's get started. Let's draw ourselves a neater diagram here and see if we can come up with something. So here we have our normal vector, call it n. Okay, we were using lowercase letters for the direction vectors, so let me use uppercase letters here. So let's say we call it ABC. Okay, we need a known point on the plane, so x naught, y naught, z naught, and I'm going to create a vector to any other point on the plane x, y, z, and these two vectors are going to be perpendicular, and so the dot product is going to be equal to 0. Okay, so in other words, okay, if I take my vector n, which is a, b, c, say, and I dot it with the vector joining the given point and the general point. So again, remember second minus first, so dotted with x minus x naught. Subtract the y values, y minus y naught. Subtract the z values, z minus z naught. So now I've created this vector that the dot product of these vectors has to be 0. And essentially, this is an equation for my plane. Okay, so what do I need to know? I need to know the normal vector or a normal vector. Hopefully you can see that, this is also a normal vector, that's also a normal vector. So anything in the direction that's perpendicular to this plane is going to work. Okay, so I need to know the normal vector and I need one point on the plane. And so my x, y, z, those are going to represent the coordinates of any other point on the plane. Because even if I had chosen this as my x, y, z, remember that this vector would have still been perpendicular to the normal vector. Okay? Now this isn't exactly the nicest way of describing a set of points. So I don't think it's going to be too surprising that we're going to try to do some algebra here to try to clean it up a bit, see if we can come up with something a little nicer. Okay, so take the dot product, which we know we multiply the components and then add them together. So we have a times x minus x naught plus b times y minus y naught plus c times, oops, I was thinking ahead, c times z minus z naught, still equal to 0. In fact, we can keep going a little more. Might as well clean this up a bit. So I'll distribute here ax minus ax naught plus by minus by naught plus cz minus cz naught equal to 0. And this is where I want you to look at this equation here. And I want you to think about whether that looks familiar to you. Okay, I'll let that sit for a couple of seconds. Does that look familiar? Okay. Now, if it does look familiar, you're not going to be surprised by what I do next. If you haven't seen it yet, maybe what I do next will give you an idea. I'm going to group together, I'm just going to use my commutativity of addition here to just kind of rewrite this in a different way. So I'm going to bring these three terms together, ax plus by plus cz plus, and I'll just put them in brackets, the sum of these three terms, negative ax naught minus by naught minus cz naught equal to 0. This is when I realized, well, wait a minute, x, y, and z, those represent variables because they're the components for the general point on the plane. But a, b, c represents the components of the normal vector, which is something that has to be known. And x naught, y naught, z naught represents the component of the point that I know on this plane. And so this whole expression in the brackets is just a constant. Okay, this is just a constant because these are all known values. So you know what? Let me give this a name. Why don't I call this D? And then all of a sudden I realize that I've got an equation that looks very, very familiar. Doesn't that look exactly like the standard equation of a line, except with this extra z component? Now, if you remember back last week, we actually tested this out as a possible candidate for the equation of a line in 3D. And we figured that it wasn't a line. It couldn't be a line because when we took a bunch of points, we noticed that they didn't all lie on the same line. But now we see that this standard equation, when we add the z component, doesn't represent a line. It in fact represents a plane. So kind of also indicates that there's some real importance to the idea of a plane in 3D. And in fact, you can think of a plane as the 3D version of a line. Okay? Now, if you remember, even earlier on, and this was a few weeks ago, where we had solved a problem whose answer kind of looked like this. We had an answer where it came out to be like 2x plus 3y minus 2z, plus 6 equals 0 or something like that. And the question was, what did this represent? Well, let's just remind ourselves, I think I might have spoken about this already. This was the answer we got to the question where we said, what are all the points that are equidistant to two given points? Okay, in 3D. Okay, and we realize that, well, that point right in the middle is equidistant, but that's equidistant. That's almost maybe thought maybe it was going to be a line right down the middle, but then you realize that a point up here is also equidistant, and the line down there. Well, guess what? It turns out that all the points that are equidistant to those 2 points is in fact the points on a plane. It's the plane that's right between the two. Okay, so we inadvertently saw the definition of a plane in this problem here. Okay, now what's going to be nice about this equation of the plane is, guess what? There's only one, what we call Cartesian equation of the plane. Okay, we don't use standard equation. We use Cartesian equation of a plane. Okay, sometimes also called the scalar equation of a plane. But what's important to realize is that these values here, the a, b, and c, the coefficients of x, y, and z, have a physical meaning. And so now you're kind of seeing I didn't choose this a, b, and c by accident. Okay, I kind of knew we were going to get to something that looked like our standard equation of a line. Here, a, b, c is the normal, or I should say is a normal vector to the plane, is a normal vector to the plane. And what we're going to have is a much more user-friendly equation than the vector equation. Okay, so before we go on to the next video, let's do one question. And I hope you realize that this is the exact same plane that we were working on before, passed through these 3 points P, Q, and R, except now we're going to determine the Cartesian equation. So again, we still have these 3 points, P, Q, and R. Okay, the question is, these are on the plane. How am I going to get a vector that's perpendicular to the plane? So I'll give you a hint. We're still going to do something similar to what we did before. We're still going to find these direction vectors. But you might think, well, why am I finding direction vectors? I don't want direction vectors on the plane. I want a vector that's perpendicular to the plane. So I'm going to give you a second to think about it. How in the world can I use these two vectors to get this perpendicular vector? Well, remember, if this normal vector is perpendicular to the plane, it has to be perpendicular to both of those vectors on the plane. And didn't we learn something that provided a vector perpendicular to two given vectors? It's going to be the cross product. So I forewarned you that that cross product was going to turn out to be extremely useful for us. And this is where it's going to be, or at least one place where it's going to be very useful for us. If we have two vectors on the plane, we can use the cross product to create my normal vector. So let me again take my vectors PQ. Okay, so what do we have? PQ, so -2 minus 1, -3. 5 minus 1 is 4. 3 minus 7, -4. Okay, and then we'll take the vector QR. Again, I could take any two vectors on the plane. Okay, so 2 minus 1 is 1. -2 minus 1 is -3. And 4 minus 7 is -3. And now I just need to take the cross product of these two vectors. Okay, so I have them one on top of the other, so -3 and 1. So my normal vector is just going to be the cross product of these two vectors. Okay, so let's see what we have. So this is going to be -12 minus, well, this is just going to be 12. So -12 minus 12, -24. Okay, this is going to be -4 minus 9, -13. Okay, and here we have 9 minus 4 is going to be, 9 minus 4 is going to be 5. And there's my normal vector. So the question is, how am I going to come up with this equation? Well, remember what these three components represent. They represent my A, B, and C values. What do X, Y, and Z represent? Well, those are just the components of any point on the line. Hey, I've got lots of points on this line I could use. So in other words, I have everything except for that D value. All right? So once you have the normal and once you have a point, it's just a matter of inputting all of this into your Cartesian equation and solving for D. Kind of like what you would have done with the standard form in, you might have done with the standard form in 2D. Okay, so here I've got AX plus BY plus CZ plus D equals 0. So A is equal to -24 times, well, I'll use this point here, times 1, plus my B value is -13 times Y is again 1, plus my C value is 5 times my Z value there is 7 plus D. And so now I can just calculate my D value. So let's get our calculator to make sure we don't make any silly mistakes here. Okay, so here we have -24 minus 13 plus 35, and we have -2. So if we bring that to the other side, D is just going to be equal to +2. All right, so my final equation is just going to be -24x minus 13y plus 5z plus 2 is equal to 0. Okay, and there you have it. Now, A couple of things that I don't think are going to be too surprising, okay? That as we would have done with standard equation in 2D, you want this to be in simplified form. So if there's a common factor between all of these, okay, you should be factoring it out and dividing it out to both sides, okay? So in particular, remember, this is a vector that's perpendicular to the other two. Had this been -24, -12, and 6, I could have taken a simplified version of that vector, okay? Would have made simplifying the equation easier, okay? Now, the other thing that is not as strict a rule, but sometimes, some people like to take this as a convention, is to keep the first term positive. So you could certainly rewrite this as 24x plus 13y minus 5z minus 2 is equal to 0, okay? This one I won't be as strict on, okay? And of course, nothing stops you from writing the constant term, bringing it to the other side of the equation. That's also acceptable, okay? So now we see that we have two ways to describe the equation of a plane, all right? This is going to be the one that we're likely going to use more often. Okay, so the last video is just going to be some further examples. That's it for this one.